Welcome back, class, and again we're going to discuss chemical nomenclature, or how to name chemical compounds. And again we're focusing on inorganic chemical compounds, and today we're going to continue our discussion dealing with ionically bonded substances. There's several different things that we're going to have to add over the next couple days, and today we're going to add dealing with compounds that are typically typically transition metals or post-transition metals is where they're typically found, and these would be compounds where the metal has multiple oxidation states. That would be the situation that we're going to deal with. We already know how to name ionic compounds, and the rules are basically going to be exactly the same. We're just going to add one thing to it. So that's the nice thing is nothing really changes, except we're going to add one little feature, and that we have to add that feature, and you'll see why in just a second. So let's kind of review the rules, and then we'll also take a look at the new rule that is part of this. So the first rule, we said that with ionic compounds, we don't use the Greek prefix system when naming ionic compounds. Like we did with the covalent bonds, we use the Greek prefix system. We don't do that with ionic bonds. And I mentioned last time that that's super important to remember. And so if you did not get that down in your notes or did not write that down, that would be a good idea to remember, so you don't get that mixed up when it comes to the test or to working out some of the problems that we're going to do in class. That is of immense importance. So we don't use the Greek prefix system when we're naming ionic compounds. And remember, an ionic compound is when you have a metal bonded with a non-metal. So something on the left side of the stair step bonded with something on the right side of that stair step on the periodic table. That's what we're looking at. And before, we were only really looking at the alkali metals and the alkaline earth metals because they only have they can only have one oxidation number. And so we were using those. There are some others, if you look on the periodic table, that only have one oxidation number, but they're kind of here and there. And the majority of your transition metals and even your post-transition metals have what we call multiple oxidation states. And that's what we're going to deal with today, is how do we name them, and what if they have multiple different oxidation states? How does that affect anything? I mean, after all, it is still just a metal, so why can't we just name the metal? Which we said was our first step. The metal is always named first, and it receives its full chemical name. And that doesn't change with when you're naming ionic compounds that have multiple oxidation states. You're still going to take a look at your metal. It's going to get its full name. So whether it's an alkali metal, an alkaline earth metal, a transition metal, a post-transition metal, it doesn't matter. It's still going to be named first, and it will still receive its full chemical name. So that's the nice thing, is that rule doesn't change. If it's a metal, it will receive its full name, period, end of story. It's the thing that happens next that changes. And we'll see why in our next slide, and that is, after you name the metal and before you name the non-metal, what you have to do is you have to write the corresponding Roman numerals. So you're going to have to kind of remember your Roman numerals, or at least 1 through 7, basically. And you would have to write your corresponding Roman numeral for whatever the oxidation number is of that particular metal. You don't have to do this for any metal that only has one oxidation number, like the alkali metals. They always have an oxidation number of 1. So that's understood, so you don't need to do this for the alkali metals or the alkaline earth metals. Or there are a few other metals that are found in the transition metals or post-transition metals that have only one oxidation number. And in those cases, then you don't need to write the Roman numeral. But for those that have multiple oxidation numbers, some of them have 2, some of them have 3, some of them have 4 different possible oxidation states. And in that situation, you need to identify what the oxidation number is. And we do that by, in between the metal's name and the non-metal's name, we write a Roman numeral. And we do that typically in parentheses to kind of set it apart there. And I'll show you how that works out and why we have to do that in just a second here. And then, of course, the fourth rule doesn't change either, and that is the non-metal is named by dropping the ending and adding "ide," okay, or the suffix "ide." And so all the rules here are the same with the exception of the third one here. We added one more rule in here, and that is when you have multiple oxidation states. So as you're looking at your periodic table, it'd be handy if you had your little periodic table with you here. Looking at that, that would be a wonderful thing as you're looking along with you, and you find the oxidation numbers on that periodic table, and you'll notice as you're looking at the transition metals or a lot of the post-transition metals, they have those multiple oxidation states. So how do we name them? We just simply put a Roman numeral that corresponds to whatever the oxidation number is. So if it was the oxidation number is 2, then we put the Roman numeral for 2. If it was 4, we put the Roman numeral for 4. That's all that changes. Everything else is done exactly the same. So that's the nice thing about naming, is a lot of our naming procedure remains the same. It's just a little quirk here or there. And as long as you can remember those little quirks, then you're fine. Here's an example, okay, of why we have to use the Roman numeral system, or sometimes it's called the stock system. I've heard it go by both, so whatever you want to call it is fine. They used to be named in a slightly different way. Used to be you would name or add a suffix to it. And so an "ick" or an "us" to it. We don't do that necessarily anymore because as time has gone by, we've discovered more and more oxidation states. And so two suffixes don't necessarily work anymore, even though you will see that occasionally. Here's our problem. If you'll notice, if we name this the way we learned in our previous presentation, we have iron with each of these. And then you have oxygen with each of these. But you'll notice they're all different compounds. You have the first one there, which is just FeO. Okay, so there's one atom of each of those elements, and they're bonded together. And we call it, if we named it like we learned before, metal gets its full name, so it'd be iron, and you drop the ending of the nonmetal and add IDE. It's iron oxide. Okay, great, that's nice and simple. But guess what? There's another way that we can write the compound dealing with iron and oxygen, and that is Fe2O3. And if we named it the same way that we learned last time, well, the metal will get its full name, iron. And since we don't use Greek prefixes for ionic bonds, then the 2 and the 3 wouldn't, have a di or a tri or anything like that. The oxygen drops its ending, and you add IDE, so we also call it iron oxide. And you're beginning to kind of see the problem. You have two different compounds with the exact same name. And then the third one there, again, you have a third way that you could write iron oxide. This one's not as common, but it can be written this way as well. And again, the same thing. You name the metal iron, and then we're not going to use tri because we don't use the Greek prefix system, so it'll be iron oxide. So all three of these are iron oxide. So the problem would be, let's say I asked one of you, my students, to go. We were doing a lab, and I wanted some iron oxide. We were going to use that, and in this particular lab, and I said, hey, go get the iron oxide. You might be faced with a little bit of a problem because you don't know which one I want, and each one of these is a unique and different compound with their own unique chemical and physical properties. And so what happens if you go back and you get the wrong one, and we use the wrong one in the experiment, that could result in some problems in our lab. And so we want to make sure there's got to be some way to distinguish one from the other. I mean, they're all three compounds. They're all three iron oxides, so how can we distinguish which one is which? And that's where the whole Roman numeral system comes in. They all are iron oxide, all three of them, but they don't have the same oxidation number, or at least the iron doesn't have the same oxidation number. And so once I know its oxidation number, then I can put that Roman numeral and identify it from there. And we'll see how this works here in our next slide. So let's take this right here. We have copper and chlorine bonded together, CuCl2. And we know that we're going to name the metal first, and then the nonmetal, we're going to drop the ending at IDE, so copper chloride. We're not going to use the di because we don't use the Greek prefix system. But Because copper is a transition metal, and if you look on your periodic tables, it can have a couple different possible oxidation numbers. I need to find its oxidation number first. So you notice I have a little equation set up here. This is an equation similar to what we use to figure out some of our oxidation numbers. We used X for copper because we didn't know what its oxidation number was off the top of our head. We know that chlorine, whenever it's bonded to a metal, has an oxidation number of -1, and there's two of them. And we know that the sum of, and that's why we've got a plus there, all the oxidation numbers in a compound has to equal 0. So we set up our equation, and of course, if you solve that equation, it would tell us that copper's oxidation number is 2. So now we can go ahead and name this. So what will we name it? Copper, the metal gets its full name. And then we're going to put the Roman numeral 2. Okay, in between the metal and non-metal. Okay, and again, that's not telling us that there are two coppers, or it's not telling us that there are two chlorines. What it is telling us is that is what copper's oxidation number is. And then, of course, the non-metal, we drop the ending and add IDE, so it becomes copper 2 chloride is how it's read. All right, let's take a look at another one. This one may be a little bit more complex. You've got manganese and phosphorus bonded together. So, at first glance, metal gets its full name, manganese. I'm not going to use the Greek prefix for either of them. And then phosphide, since I'm going to drop the ending. But I also noticed that manganese has multiple possible oxidation states. So I need to figure out which manganese phosphide am I dealing with here. And so I set up my little equation to find the oxidation number of manganese. I don't know what it is because it's a transition metal and it has multiple oxidation states. So I know there's 3 manganese. I don't know what its oxidation number is, so I put an X there. Plus, and then there's 4 phosphorus. And we know that phosphorus, because this is an ionic bond, it's going to have a charge of -3, and whatever the charge is, that will also be its oxidation number. And so its oxidation number is going to be -3. That's one of the rules we learned earlier when finding oxidation numbers. And we set that equation up. We go to solve it. We find out that manganese has an oxidation number of 4. And so we name it manganese with the Roman numeral 4. Phosphide is how we would name that. And so the manganese and phosphide, all that remains the same. The metal gets its full name. The non-metal, you drop the ending, add IDE. The only thing we're changing is once we know the oxidation number, we're using a Roman numeral for that in the middle there. So that's how that works. All right, let's do one more example. Here we have chromium and sulfur bonded together. And so again, it would be chromium. The metal gets its full name. The non-metal, you're going to drop the ending and add IDE, so chromium sulfide. But because this chromium can have multiple oxidation numbers, I'm going to have to find out what its oxidation number is. And this is why we did all that work with oxidation numbers before we learned how to name. And so I'm going to set it up. Chromium, I only have 1 of them, so I don't know what it is. X plus I have 3 sulfurs. Each sulfur is going to have a charge of -2. Because it's an ionic bond, and whatever its charge is, that will also be its oxidation number. And so I set this up, and if I solve for that equation, I would find out that my oxidation number for chromium is 6. And so what do? I name it chromium. The metal gets its full name, and then whatever the oxidation number of the metal is, I put that in the middle. And so I use the Roman numeral 6. And then sulfide, the non-metal, you drop the ending, add IDE. So that's how you name an ionic bond with multiple oxidation states, where a metal has multiple oxidation numbers. Here's one I would like you to try. We're going to go back to one of the examples I showed you at the beginning, and I'd like you to do this one on your own and see if you can't figure out what the correct name of this particular compound should be now that you know how to use that. And we'll check and see in class whether you're correct.